I'm ready to just go ahead and start, and I'm just going to go ahead and launch in with Clyde Baker, Lifetime Achievement winner for 2013, the Fazlur R Medal. You've been involved in building foundations for your career. When you look at the buildings going up today, is a foundation, or are there changes? What have you noticed?
Well, there are different types of foundations, and of course, going taller and taller puts additional stresses on those foundations, which does change the requirements. Steel is stronger than concrete. If you're going to go, when you reach the limit of the concrete strength, then you have to use more and more steel. But we're increasing the concrete strengths all the time, and so we haven't reached the limit of what we can do in concrete strength. So at the height of the buildings that we're talking about right now, up to say 1 kilometer, I don't think there are limitations. Now when you start talking about mile-high buildings and so forth, I think you then start pushing the material limits.
When you look at proposals for mile-high buildings as an engineer, after all that you've seen and been through, is it surprising to you that this has finally come along, or have you been expecting it?
Well, the ones I have seen really don't get into the foundation part, you know, I can't say much more. If they're going to go have a realistic discussion, of course, they have to get involved in the foundations. And as a foundation engineer, that of course interests me.
We're sitting in Chicago, just blocks from Lake Michigan,
right.
And I'm told that you have a story about how you intervened in a concrete pour for a tall building that was underway, and it says here, in order to prevent a disaster involving the Chicago water table. What was that? Tell us about it.
Well, I wondered about that, and when I think I saw that as a possible question, I tried to think about what particular building I would be talking about, because there have been a number of problem jobs where that could be discussed. The thing about Chicago, we have 3 water tables, and when you're constructing foundations in Chicago, any one of those water tables can create a problem for you. So, and we've had problems created by all 3.
What are those 3?
Well, there's an upper water table that's related to Lake Michigan, the sands and fills over the city. Then there's a deeper water table that's related to seams in the interface between the soft clays and the hard pan, water-bearing sands that were probably created geologically before the upper clays were deposited. Channels that were filled with sand, and water eventually seeps into them, and they can be under considerable head. And then you have the water table in the deeper rock, which is underneath the hard pan and puts pressure there. That rock water table can be high. It depends on pumping out of the rock. There's been changes in that water table from deep pumping out of the rock. So all 3 of those water tables can create problems for us. And I'm not sure what specifically that refers to. I know we have had problems with a number of those, and if I'm involved, you know, I'm out there trying to solve the problem. And I remember one project where I was called out, and it was my wife's anniversary, and she was in the car with me, and I had to go out to the job site to help solve one of these problems that you're referring to, with her sitting in the car waiting for me. great support.
An engineer's wife.
Yeah, an engineer's wife. That's what you have to do, yes.
Because one story that I've heard that is not associated with your work, I don't believe, was the John Hancock Center.
Yes.
Which of course, again, is only blocks from Lake Michigan, that when they were doing some work in the basement and dug through the floor, they punched through the membrane and the water came gushing up. How do you even begin to deal with a problem like that?
Well, there's two basic engineering design procedures. One is you design to handle the pressure. For instance, if you're using a mat, you've got usually enough, and the mat's connected to foundations, you usually have enough pressure potential to resist any hydrostatic uplift. The other approach, if you don't have a mat, is to provide drainage. And any seepage that gets into your drainage system is carried off. So those are the two engineering approaches to solving that problem.
The biggest challenge you've ever undertaken, tell us about some of the projects that you've worked on and what are the most memorable for you?
Well, I have to say the most memorable for me, and it's not in Chicago, but a lot of Chicago ones are memorable, but the most memorable for me was the Petronas Towers in Kuala Lumpur. And if you see my talk this afternoon, I show a picture of the profile there. And they were trying to build, at that time, the world's tallest building over karstic limestone. And if you ever visit Kuala Lumpur, they can take you to caves to show you the caves in this karstic limestone. And then they're talking about building the world's tallest buildings above this, right? So you initially think, my gosh, that seems crazy. But there was a reason why they wanted the buildings at this particular location. And they also had a requirement. They didn't want any differential settlement. Well, you can't do that, you know. So we got them to agree on a design limit of a ½ inch of differential settlement across the mat. And that's what we had to design for. And that created all kinds of problems for us to be sure that we could do it. And it did involve a massive grouting program to fill up the voids in the karstic limestone below us to some depth. And the question is, how deep do you go? And so we adopted a conservative procedure on how deep to go, and oversaw the grouting program to that depth. And everything worked out fine, and the settlement was less than we predicted. Of course, everybody's happy when the settlement is less than you predict. But that was probably the most challenging project.
Well, and a ½ an inch over
1,500
meters, yeah.
Yeah, 50 meters.
It doesn't sound like much, but it's big.
Oh, well, no, it isn't. It isn't much until you're talking about something that's very tall.
Right.
And then if you've seen the Petronas Towers, there are two of them, and they're connected by a bridge. And the way they do that, one end of the bridge is fixed, the other end of the bridge can move in and out of the tower. And they have to provide that because the winds don't act, you know, it has to have some independent action. And that's a fascinating, that's structural, not geotechnical, but it's a fascinating solution to a very difficult problem. And my wife and I have been on that bridge, and it's very fascinating. We haven't never been there on a windy enough day to see it moving in and out of the building. I don't know that we want to do that.
I don't know. That's a good question. The Petronas Towers project was the one famously where they discovered the bedrock all of a sudden.
It goes like this. It creates a canyon like this.
Right.
It goes like this. And they're building one tower on one side and the other tower on the other side. So there's going to be a natural tendency because of that canyon for the foundations to tilt like that. So how do you prevent that? And it was prevented by putting the building on. Initially, it was going to be board piles. It turned out to be barrettes, which is another way of making a hole in the ground to go deep. And then you fill those holes with concrete, and you control the settlement by controlling the distance below the foundation and to the rock, and then you have to grout the rock below. And you do those two things, and we were able to meet the design requirement of less than a half-inch differential settlement.
What other of the super talls have you been involved with?
Well, the other one that everybody thinks about, of course, is Burj Khalifa, and we were one of the peer reviewers for our involvement was as a peer reviewer for the architect firm Skidmore, Owings and Merrill on that one, and then we've also been involved in Taipei 101, which was up there. And you know, the categories keep changing, and people ask me, well, how many tall buildings, super tall buildings, have you been involved in? And I used to say 8 of the 12 tallest or something.
Not anymore.
Now it's like 7 of the 20 tallest, or you know, they keep building them taller and taller. So my part keeps going down. But a couple of tall buildings in Korea, Incheon 151, and let's see what else. And well, then I come back to Chicago, and we got the foundations in the ground for it anyway. It's a beautiful looking structure, the Calatrava designed spire, and that's designed as a super tall to support a 2,000-foot tall building, which qualifies for your super tall.
And you did your part.
Yes, we did our part. The foundations are in there, and they will hold up whatever you want to build on it. And someday somebody will decide they're going to finish it. But
any particular challenges there? Because here again, you're right next to the Chicago River. You're right on the lakefront. I'm sure you dig a hole, and pretty soon it's going to fill up with water.
Well, that part has been solved because of the diaphragm wall built around the site down to good impervious clay, and so you still get rainfall into it and that sort of thing, but you know, there was going to be a mat down there at the bottom, and on these deep caissons that go to rock, so it's designed. I forget what somebody said. How many millions of dollars have already been put into those foundations, but it's a big number. Right now, somebody might say it's a very large swimming pool.
Well, that foundation was designed for that particular building, and
yes.
We all know the design, the circular kind of drill bit that people call it. Is that foundation easily adaptable to be used for other structures?
Well,
what kind of accommodations would have to be made?
Yeah, you'd have to do some accommodations, I would think, but the way you could handle it is you'd have to span to those foundations that are already in, and then whatever you put above it, that's up to you. But you would have to span to the foundations that are already in. There's a lot of money in those foundations, and they're capable we proved them capable of carrying the largest pressures that have ever been used in Chicago by more than 50%. I mean, so it's the allowable bearing we proved was 300 tons per square foot, which is a very high allowable bearing. So those you can build very tall on top of those foundations, and it doesn't have to be the same Calatrava designed superstructure, but you will have to, whatever you design above it, you will have to transfer to the existing foundations.
For those wanting to get into the geotechnical field today, they have technology and materials to work with that I wonder how you could have imagined those when you started out. Any advice to them, and what differences do you see just in the tools that they have now versus what you had, a slide rule going in?
Well, the tools can be dangerous too. I mean, basically it's the computer that's ability to do anything. But it's what you put into the computer program is still important. And what the computer enables you to do is to do lots of what ifs. You put these properties in and you see what you get. And so you can see how it's going to behave a heck of a lot easier than certainly we could in our day. But ultimately it still depends on the properties that you put into the program. And I always like to tell people, before you do the fancy finite element program, do a simple calculation based on the data you have and see what answers you get. And that gives you a gut feel, because that you got control of. You can do that on your slide rule or your calculator or whatever. And that you have control over. And see what you get. You get a reasonable answer. Now go to your finite element programs and do what you're able to do with those finite element programs. And see how they compare. The projects that I've been on, actually, my efforts at doing simple calculations have compared very favorably with the ultimate output with the fancy finite element programs. And that just comes from experience. My advice to young people would be two things. Associate with good people, and then get field experience. If you associate with good people, they're going to help you. They're going to help you get ahead. And you're going to learn from them. And then you need the field experience. And if you do those two things, and always build on the experience of others. Check the case histories in the area. What has been done here? What was assumed, and how is it performed? If you're in a similar geology, that's the best information you can have. And so those would be my recommendations to young people.
So trust your gut, use your slide rule,
first,
and get out of the office.
No, well, actually that's oversimplification. Get out of the office, yes, but know enough to be able to use your slide rule and make simple calculations. But today you have to know the computer programs. You have to be able to work with a computer if you're a young engineer going out today. You can't do it the way I did it. You have to be able to use the computer. And of course, what I observed is all the young people are very good at it. So I don't think there's any problem there. I do think the associating with good people, get good mentors, and build on what experience has happened before in that area, and then get out in the field. Those are all good points to make.
Great. Thanks very much. That's what I got. Terrific.